Okay, which number on the multiple choice?
All right. I have a couple. The first one is number 38.
Number 38. Doo-doo-doo-doo. All right. So we haven't talked a ton about the term electrolyte yet. We'll talk more about it next unit. But basically, a strong electrolyte is something that is going to conduct electricity.
Okay.
And so we had talked about how one of the properties of ionic solids is that when they are a solid, they do not conduct electricity, but they do conduct when they are either molten or when they are dissolved in water.
Okay.
So the best choice out of these would be whichever one of these is ionic.
Okay. Perfect. Thank you.
You're welcome.
And then on number 39.
Okay.
Or wait, no, it wasn't 39. It was 40.
You just love these structure ones, don't you?
Yes.
All right. Which statement correctly identifies diagram 1 and identifies the compound with the lower melting point? Okay, so one is sodium chloride and one is magnesium sulfide.
This one, I think I got it right. I just wanted to make sure I had my reasoning right.
Okay. So survey says answer is B. What did you say your reasoning was?
Well, it looks like the cation is smaller in diagram 2.
Yes. So the
Okay.
darker circles look smaller to me.
Okay.
I'm with you on that one.
That is good.
So magnesium and sodium have pretty close to the same atomic size because they're right next to each other.
Mm-hmm.
But sulfur should be smaller than chlorine.
Okay, so that's good.
So I'm cool with that. And then talking about melting points. So lower melting point means stronger interactions or weaker interactions?
Lower melting point would be weaker.
Yep.
Okay. And that would just be because it has a higher charge.
So the sodium chloride only has +1, -1 charges. So that would be weaker than magnesium sulfide, which has +2 and -2 charges.
Yes. Okay, good.
Yep.
And then number 47.
47. Okay. So there's a formula of 1, and there's a formula of sodium glycinate. So this one, this is a tricky question. I wouldn't worry a ton about this one. Just because there's a bunch of the other choices that we haven't talked about yet.
Okay.
So we haven't talked about an acidic solution yet. We haven't really talked about what makes things super soluble in water yet. So if you could get that narrowed down to A and C, I'd be happy with that.
Okay. And then how would you know what, like, why
So the answer is A, that's ionic, because we have the sodium plus ion and this giant negative ion.
Okay.
And C can't be it because we do have hydrogen bonding between the nitrogens and this hydrogen.
Okay. That makes a lot more sense.
Yeah.
Thank you.
You're welcome.
And then I had another question on 51.
Okay.
which was, I got the right answer, D, but I wanted to know why B and C would not work.
Okay, 4 different gases at the same temperature. So it cannot be B because, go away. The pressure does not depend on the average speed of the molecules.
Okay.
There's much more to pressure than just that.
But that can affect it, right? If everything else
So
is
the speed
same?
can affect the pressure if everything else is held constant.
Okay.
But they don't necessarily tell us that we have the same number of particles of each of these gases. They don't tell us anything else about that.
Okay.
Because if I have twice as many molecules of a gas, that's going to increase the pressure just as much as the speed would.
Okay.
The volume of the gas has absolutely no influence on its speed. The temperature is the only thing that controls it. Temperature and kinetic energy control the speed. So volume has nothing to do with it.
Okay.
Um,
Okay.
so if we know they're all at the same temperature, then the only thing that can affect that speed is the molar mass.
Okay, that makes sense.
Can we go over number 33?
On the multiple choice?
Yes.
33. Of course. So 33 says, given the density of mercury at 0 degrees Celsius is about 14 grams per milliliter, which of the following is closest to the volume of 1 mole of at this temperature? Ooh, we gotta do a little bit of math here. So 14 grams per milliliter mercury. So if I've got 14 grams per liter, and it says that I have 1 mole of mercury, this is just doing some stoichiometry or some converting, I guess. So if I have 1 mole of mercury, oh my goodness, can you believe I don't have a periodic table anywhere near me? What is going on? I do have one on my phone. Periodic table tells me that the mass of mercury is, because this is a multiple choice question, I'm going to round it. It's about 200 grams. Oops, that doesn't go there though. Come on. 200 grams of mercury is in 1 mole. And then they said the density is 14 grams for every 1 liter. So 200 divided by 14 is kind of hard without a calculator, but we could round it. We could do 200 divided by 15. That might make it a little bit easier. So 200 divided by 15 is close to 13. What are my choices? Well, 200 divided by 14 has got to be bigger than 1. So it's not going to be A or B. C is too close to a little number. 200 divided by 14 isn't going to be 1. And 28 times 14 would be way bigger than 200. So I'd go with D.
Okay, that the milliliters with the -1 for the exponent just kind of confused me.
So anytime you see something with a -1, that means it's over. So milliliters to the -1 means per milliliter.
Okay.
Wait, wouldn't that mean that it would be grams per milliliter then, not liter?
Oh, crud. You're right. I am so wrong. That's 14 grams per milliliter, wasn't it? Ignore everything I just said, Alex. Nope, that's it. And then there's 1,000 milliliters in 1 liter. So it would be one of the tiny numbers.
Oh, it says the answer choice is D. Or the answer for it is D.
Did I misread something? Oh, because the choices are in milliliters.
Oh, okay.
Whoa, okay. So I'm fine. I wasn't totally crazy. So we don't need any of that mess. It's just per milliliter instead of per liter. So we'd still be fine. It'd still be 14. Ish.
Okay.
Whoa. Sorry about that. All right. What else we got? Anybody else have questions about from the multiple choice since we've got it open?
Can we go over number 71?
71. Scrolly, 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 scrolly. I promise you the next chapter will not have this many problems. All right, 71. So we get a whole bunch of ionic radii based on Coulomb's law and the information in the table above. So there's our hint, right? Coulomb's law.
Okay.
So they're telling us we need to think about either charge of atoms or size of atoms. Which of the following anions is most likely to have the strongest interactions with nearby water molecules in an aqueous solution? So strongest interaction is going to be highest charge or smallest molecule.
Okay.
Or the best combination of those two.
Okay.
So I would go with sulfur because it's got that higher charge, but it's the smaller of the -2 ions.
Okay. So would you say that the charge is like has more of an effect on it? Because I had picked chlorine at first because it was smaller.
But it only has a negative charge. So by picking sulfur, we're picking the smallest of the highest charges.
Okay.
So if we have the option, we need to hit both of those.
All right.
Can I ask about question 56, please?
Yeah. 56. All right. So 3 containers, A, B, and C. We're talking about density. So density is grams per liter, right? So if we look at these 3 gases, they
Yes.
all have different molar masses. They're all at the same temperature. But gas B has a
Sorry to
higher.
interrupt. But am I the only one who can't see like your screen right now, or I don't know? All I see is the whiteboard.
Oh,
Oh, yeah.
well,
I do too.
never. Well, thank you. Thank you for telling me. There. Now you can see. So they're all the same temperature. B has got a higher pressure. So we have to think about masses and volumes, right? So, well, they don't tell us how many moles of each we've got. So let's just assume we've got a mole of each. Sound good, right? If we would, can I draw on this? Is it gonna let me draw? No, I thought it might let me draw if I open up the question. So we have to do a quick little Puvnert thinking of thinking about volume. So if we think about the fact that PV equals nRT, they all have the same temperature, so that's not going to affect anything. Let's assume they all have the same moles. R is going to be the same for all of them. If we're trying to figure out volume, the pressure on flask B or container B is twice as big as anything else, right? So
Yeah.
if its pressure is twice as big, then its volume is going to be half the volume of everything else. So if we're trying to figure out grams per liter or milliliter, it doesn't really matter either way. It's got the middle mass for molar masses, but if it's got half the volume, it would have to have half the grams of anything else to work out to be the same density. And that's not going to work out. So if we've got $16 grams over a liter versus 30 grams over 0.5 liters versus 58 grams over, oh, I lost my numbers now. 16, let's go easy. Let's pretend. I'm sorry, my computer is misbehaving. It's making me click extra times. So if it was 16 grams for 1 liter, 30 grams in half a liter, or 58 grams in 1 liter, 58 grams. This is going to work out to be the biggest density.
Okay.
Because this is going to be, the 16 out of 1 is going to be smallest because that's going to be 16. 30 divided by 0.5 is going to be 60. And 58 divided by 1 is 58. So it just barely beats out Flask C.
Okay. Is there any like relationship between like density and like the Pivnert stuff, or is it just you have to do the math?
I mean, you kind of, relationship meaning like straight up if my pressure gets bigger than density does something.
Yeah.
There is,
Can I
I mean, you can substitute in, I think we did this in the notes where you can find the density equation if you plug in little m over big M, the grams over molar mass for moles. And you get MRT over P. No, that's wrong.
I set it up in the equation MP over RT, and that's how I solved that problem.
Yeah, that's the way it should be. I was trying to solve for molar mass instead. Yeah, PM over RT. So I mean, I suppose you could make a relationship with that. So going, in our case, because the pressure was bigger, times the molar mass would give us the biggest density. Because
Could you
that
do
R and the
that
T would be the same. You could do that.
for like everything solving with density?
Yep.
Okay.
I was also wondering if you could help with mastering chemistry question number 14.
Ooh. Is it okay if I hold on to that one for a sec, Natalie, and make sure that we're good with the other multiple choice?
Yeah.
Okay.
I have a few multiple choice questions.
All right, let's go ahead and hit those first.
Okay, so first number 79.
$79. Okay. Yeah.
Okay, so I got it down from A and B, but I didn't know why D was right over A.
So the reason why A doesn't work is because the hydrogens are not connected onto a nitrogen, oxygen, or fluorine in their compound. They don't have that bond to a nitrogen, oxygen, or a fluorine. This hydrogen is still connected is still bonded onto a carbon. Even though it looks like it's making that intermolecular force with a nitrogen, an oxygen, or a fluorine, it needs to be bonded to those atoms.
What do you mean? Like, how would you know?
So this, I can't draw on here, but this hydrogen
Mm-hmm.
is actually bonded onto a carbon. And so that difference in electronegativity isn't high enough to make a hydrogen bond. Hydrogen bonds only happen to hydrogens that are bonded onto a nitrogen, an oxygen, or a fluorine.
Okay, because the one in D is connected to that end with the solid black line.
Yep. So those solid black lines represent actual bonds.
And then what is the dotted line showing?
So the dotted line is showing the intermolecular force.
Oh, okay. That makes more sense.
Yep. So this one
Okay.
works because that hydrogen is actually physically bonded onto the nitrogen, and then it's being intermolecularly attracted to the oxygen.
Okay.
And that's one of those three atoms that can work out. What else you got, Alex?
I just wanted clarification on number 42, I believe. Okay. Okay, because I thought that when it hit the walls of the container with less force, I didn't think that mattered, like the amount of force.
Yes, it does. So
Okay.
pressure comes from both the number of collisions and the force of those collisions. So that's why when we slow down the temperature, when we reduce the temperature, we are making those molecules move slower. And so when they do hit the container, they're hitting with less force.
And that just depends on temperature?
Yes.
Like there's no size involved in the force?
So no, there is no mass component to that force.
Okay. Thanks.
Yep. Any other multiple choice questions while we're here? All right, we can always come back if you think of one. So let's get to mastering Chem. Never remember my password. All right. Natalie, which question was it?
14.
14. Right. Okay. Was the math just not working out?
Yeah, I just couldn't figure out how to do it.
Okay. So this is one of the Dalton's Law of Partial Pressures questions. And since they're giving us moles, we can find our mole fraction. So I'd add up 0.220 plus 0.350 plus 0.640. That would give me my total number of moles. And they just want the pressure of oxygen. So I would take the moles of oxygen, the 0.350 moles, divided by the total number of moles in the mixture, all three of those added together. And then if you multiply that by my total pressure, that will tell me the partial pressure of that oxygen. Because remember, one of the things that Dalton's law says is that whatever fraction of the mixture the gas is, it will also provide that fraction of the pressure.
I don't know why I wasn't getting it. Like, I kept doing it and just the math wasn't working. I spent forever trying to do it yesterday.
I don't know. Right. Remember that questions like this would be pretty common to have on a multiple choice because it would be, they could give you numbers that would work out really easily for the math that you wouldn't need a calculator for necessarily. All right. What else do I have questions about? And it would be fine if you've got questions about like a topic in general rather than a specific question. We can go over that too.
I have a question. Sorry.
It's
You
fine.
can go
Go
first.
ahead. No, you go ahead.
Oh yeah, I have a question about the packet.
Okay.
It's on page 19 and example number 36.
Okay.
Yeah, I'm not really sure how to solve that.
Okay. So this is a problem where they're just sort of like throwing a bunch of numbers at you. We got to figure out what's going on. So it says we have a sample containing a certain number of moles of argon at a given temperature and a pressure, and it is heated to a different temperature. So when you see that this one isn't quite as obvious because it doesn't say we changed the temperature, but we can see that the temperature is changing. Anytime you see a change like that, or it says calculate the change in volume, that means we're going to use the combined gas law.
Yeah, I have the thing set up to look like yours. I just didn't know how to approach it. Like
Oh,
how
because this is the one, like, because we're comparing it, how much it changes. It's sort of an awkward thing. I haven't seen this show up on an AP style question before. When I solved it, I just said, well, so volume 2 would have to be this many times bigger than volume 1 because there's 2 variables in there.
So, how did you calculate it? Like, what were your steps?
Ooh, okay. So, first thing I did was I cross multiplied because I like cross multiplying. You could also just go ahead and take, 568 divided by 286 and simplify that, and then 897 divided by 329, simplify that, and then I divided both sides to get V1 by itself.
Oh, okay. I didn't see the V2 there as,
Oh, he is right there.
yeah, I thought it just, no, in your answer, I didn't see the V2. I just saw it now. Yeah, I was wondering where it went.
It's right there.
Okay, thank you.
Yep. That question would probably be more likely to be, they would give you a volume, like they give you a V1 and then ask you to find what V2 would be. I've seen that way much more often. Alex, what were you going to ask?
Can we go to the multiple choice, please?
Yes.
Number 82.
All right.
Okay, so I found out why E was the answer and why D wasn't. But A, B, and C, I was kind of confused on like how you would figure out those weren't.
Okay. 2 flexible containers for gases are at the same temperature and pressure. One holds 5 grams of hydrogen and the other holds 8 grams of oxygen. Which of the following statements regarding these gas samples is false? Okay, so that means that A, B, and C are true, right? Because we're not picking them as the false ones.
Right.
So the volume of the hydrogen is the same as the volume of the oxygen. This is true because they're at the same temperature, the same pressure. Half a gram of hydrogen would be, so if it's half a gram of hydrogen, the molar mass of hydrogen gas is 2 because it's H2. So that would be basically 1/4 of a mole of gas, right?
Yeah.
And same thing for oxygen. If I have 8 grams, molar mass of oxygen gas is 32. So that's also 1/4 of a mole.
Okay.
So since they have the same number of moles, the same temperature, the same pressure, it means the volumes have to be the same. Because that would be like plugging it into Puvner. All the variables are all the same.
Okay.
B, the number of molecules in the hydrogen container is the same as the number of molecules in the oxygen container. Might have been a little bit easier if B was first. So
Yeah,
again,
it's
if we
just
have
the same.
if we have the same number of moles, they're going to have the same number of molecules.
Okay.
And then the density of the hydrogen sample is less than that of the oxygen sample. That would be true because density would be grams per volume.
Okay.
And so if A is true, then they have the same volumes. 0.5 grams divided by whatever that volume is going to be a smaller number than 8 grams divided by that volume.
Okay. Thank you.
Yep.
Can you explain what the difference is between speed and kinetic energy?
Yes, I will try my best. It is it's complicated for us silly little human beings because we don't talk about energy very often in everyday life. Energy is not something that has a tool that can measure it. So the closest thing that we have to talking about energy is temperature. That's sort of how we measure a change in energy, is by measuring the temperature of something. So when we're talking about kinetic energy, we're talking about how much force has been given to those particles by changing their temperature, or by giving them the energy to keep them at the temperature that they're at even. The speed talks about how fast those particles are moving. And so kinetic energy is only dependent on temperature. If two particles have the same temperature, they're going to have the same kinetic energy. They will not necessarily have the same speed, because speed is also controlled by mass. So the thing that I always sort of compare this to is if you were a fantastic soccer player, you would be able to control the force of your kick so that you could kick a ball with the same force every single time. And so if you can do that to a soccer ball, then the soccer ball is going to travel about the same speed, about the same distance every single time you kick it. Now, if all of a sudden you kicked a tennis ball instead of a soccer ball, that tennis ball has much less mass than that soccer ball does. It is going to travel at a much faster speed from your kick, even though you are giving it the same amount of force, the same amount of energy as you always do when you kick a soccer ball. Does that help?
Yeah, thank you.
Okay. Yeah, because we like in life, we never talk about force or energy very often. We normally talk about speed and temperature much more.
Can you go for 84?
Yeah. Right. All right. So this is talking about, what behaves more like an ideal gas or less like an ideal gas. So at this point, we're only talking about hydrogen gas. So we're not comparing things about masses or sizes or intermolecular forces or anything like that. This is just trying to figure out how we can get that hydrogen gas to behave most like an ideal gas, which means that we want it moving really fast so that it can't stick to itself. And we want it at a low pressure so that we're not starting to condense those molecules together and get closer to a liquid. So we would want the highest temperature and the lowest pressure. And so highest temperature would be the 500 Kelvin, and between those two, my lowest pressure is the 0.1 atmospheres.
Thank you.
Yep.
Can we go to number 93, please?
93.
I know why the answer is right. It's just the explanation for why.
Okay. So why more energy is required for the process occurring at 110 Kelvin than for the process occurring at 90 Kelvin. So at 90 Kelvin, we're going from, so we didn't talk a whole lot about these graphs, but just to let you know, where P is, it would be a solid. Where R is, it would be a liquid, and where T is, it would be a gas.
We did those last year.
We did them last year. AP doesn't expect you to be able to read these anymore. So this is my fault for giving you an old, outdated question. I apologize. But so basically, and even if you look really close, let's see if I can make this bigger. Nope, of course not. If you look really closely, there we go. So at 90 degrees, it says delta H. See where it says FUS?
Oh yeah.
That stands for,
I can't see that on the paper.
yeah, that stands for fusion. And this one says vape, so this stands for vaporization.
Okay.
So at Q, we're basically melting if we're going up. So it requires less energy to melt something because we're not totally breaking all of those intermolecular forces. But when we go from a liquid to a gas, that requires much more energy added because in order to go from a liquid to a gas, you have to break apart all of the intermolecular forces. You have to break every single one of those molecules all the way apart.
Okay. Thank you.
Welcome. Anything else? Right. I'm going to assume by the fact that no one is talking that we about maxed out our questions. We're going to have time to work in class Monday and Tuesday on stuff. I might have a couple specific things we're going to do, but for the most part, if you've got questions, we can clear them up then too. So unless anybody wants to jump on real fast, I'm going to call it for tonight. We're good? All right. Well, have a good night, y'all. Get some good sleep, and I will see you tomorrow.
Thanks, you too.
Bye.
Bye.
Thank you.
Night.
Bye.
Bye.